Hello world, this is CS50 2D. Welcome back. This is lecture 1, Flappy Bird. So we're doing the zero indexed approach to the course titles. Last time we did Pong, which was a bit of an older title from the 70s, and this week we're going to be exploring something a little bit newer. Maybe a lot of folks actually got the chance to play it themselves back around 2013 or so, called Flappy Bird, which kind of had a bit of a controversy around it as well, related to, I believe, the pipe graphics had been stolen, something to that effect. But a lot of people, for a brief period of time, were really enjoying it. I got hooked into it as well. I was playing it for a little while. I wasn't very good at the game. I don't remember. I had friends who were very, very enthusiastic about it. But this week, thankfully, Flappy Bird is a simple enough example that it allows us to sort of evolve from Pong, because last time when we were looking at Pong, it was just essentially shapes, rectangles, and just white and an off black color. But this week we want to actually begin looking at a lot more interesting things. Things that'll take us to not just shapes, but rather things that are 2D artwork that move around on the screen. Namely, with what we also alluded to last lecture, which are sprites. And so a sprite and an image are kind of interchangeable. A sprite is essentially typically an image that will move around on screen, and people, when they think sprite, they'll think of, oh, a character graphic or maybe a fireball or something versus what might be a background texture or the like. But we'll be looking at images and sprites. We'll be looking at scrolling, so this is a very common device used in games, and parallax as well. And we'll also take a look at this sort of like idea of using illusions in games to affect all kinds of this sort of verisimilitude of sort of feeling like we're in a world that's not actually there. The also procedural generation aspect of the lecture will be tied to the pipes. If people recall, Flappy Bird is a game where all these infinite pipes are scrolling through the level. And randomization we looked at last week is a very important piece to making sure games are dynamic. And that's also something that I've always found very interesting, procedural generation in particular. And this course will explore that in various iterations. This week is very simple in as far as we're just essentially dynamically altering a Y value of pipes that scroll through the screen. But we'll get a lot more sophisticated with that even next week when we look at Breakout. State machines are something we talked about briefly last lecture, and it was just essentially a flag, this sort of game state, a string variable rather. And this week we're going to properly create a construct that lets us model state machines a lot more abstractly, and also avoid a lot of these sort of like conditional string checks in our code. And then lastly, well, for fun at the very end, because this was a mobile game to start with, last time we only looked at keyboard input, but Flappy Bird and all mobile games essentially use touch input on devices, and that we can model with mouse input through Love2D. It has a couple convenient functions for that. A couple of just fun little articles and blog posts and things that I decided to include here. Actually, this top one's a course, and this one is kind of a blog/course page. But when I was initially getting used to Lua-based programming and Love2D, both of these resources were of a lot of help to me, and I really like them a lot. I encourage people to check them out. In particular, how to make an RPG, as the name implies, is about making RPGs. Some of the things we'll look at towards the end of the course, like Pokemon, that will be more applicable to. And then game programming patterns. We've used Robert Nystrom, a couple of his graphics and links in the slides so far, but can't recommend folks taking a look at that enough. So our goal today is just going to be, as I sort of described verbally, this recreation of Flappy Bird, not using the original artwork, but rather some open source artwork, and all of that's been linked in the source code. But you can see here, it is essentially the same game. It has just a small bird whose goal is to jump up and navigate this sort of randomly generated obstacle course. It's also got a ground and a background. These are going to scroll at different rates to give us this parallax sort of artificial look as if we're in a space. And rather than, I think, purely verbalize it, I would like to demo an example of that. But last time I demoed it on my own, could we perhaps get any volunteers to take a look and demo it? Yeah, why don't you come on up? What's your name?
Hi, I'm David.
Colton, nice to meet you.
Nice to meet you.
Okay, so I'm going to go ahead and hit Command L here to start this.
Okay.
And so why don't you go ahead and give it a shot?
All right, hit enter.
Enter will start it.
Okay, and then how do I play?
And then spacebar is going to be to jump, and you want to make sure the bird doesn't hit the pipes.
All right, here we go. How hard could this be?
I think it's pretty hard.
All right, here we go.
Ooh, okay.
Oh, what's my score?
We have a score of 0 there. So every pipe pair, we call them in the code, that you go through, you'll get 1 extra point. And so once you, as you can see, there's a state transition here. Once you lose, it shows you your score, and then you can press enter to play again. Kind of like we saw at the end of Pong.
Okay, can I play again?
Yeah, please, please.
All right, here we go. 3, 2, 1.
Oh, gotta go.
Okay, can I play
when,
again?
when you hit the ground, that's also a lose condition. Yeah,
All right.
Please,
so I have to keep hitting the space bar.
Yep.
All right, one more time.
This game was very hard when it came out. It was the reputation.
This game is very hard right now. Okay, here we go. 1 point coming. Damn it.
It's pretty tricky. Let's see if I can
right.
minimally get one. I don't even know if I can get one because I'm so rusty, but let's see. Oh, no.
I think there's a bug.
It's a tweakable height differential. We could definitely do that for the sake of speed. Also, the frame rate is a little bit adjusted for production. So for my eyes,
I think we need to get rid of that pipe.
Yeah, we'll just get rid of all the pipes. Yeah. Let's see. We'll try one last time, and then maybe for fun, we'll lower the difficulty a little bit. Oh, I got so close. Well, that's essentially the gist of the game. I mean, a lot of people, when they were playing this game, essentially had a very similar experience to this on the phone version.
Oh,
that was sort of its reputation. Yeah, a lot of losing.
All right, well, thank you for having me.
Thank you for volunteering. So I'm going to go ahead and close that. So that is in the final example in the repo, and then maybe towards the end of the lecture, if we have time, I can adjust. Essentially, there's a velocity value that gets subtracted from the bird's height. For folks like me and our kind volunteer who maybe aren't as experienced playing, it can be a little bit difficult to start. But just for the sake of demoing and showing the score improving, maybe I'll tweak that just a little touch. So let me go ahead and transition to the slide deck one more time. We're going to do things, I think, a little bit differently to last time, where the code, especially as we get progressively through the rest of the lectures in the term, there's going to be a lot more to cover and per example. And so I think I'm just going to illustrate the code and kind of go through it and allow folks to read some of it on their own at home. But we're going to do essentially the same thing we did yesterday. We're going to start working our way up from essentially scratch, just a blank window, up to the final implementation that we just saw. And a lot of things, people probably noticed a lot of things. There were, one, graphics to begin with, as we saw. We have a bird graphic jumping up and down. We have these pipes that are moving through the screen. We have this background. We have this floor. We have sound effects, which we saw last time, but what we didn't have last time was the music track. So we're also showing just a music track playing constantly, which can add a lot of immersion to a game. Very important detail. I love music myself. And we saw state transitions. A lot of the same pieces, interestingly, from Pong are applied here in Flappy Bird, but they're just used to a different effect. And so we'll see a lot of those ideas as we explore. So I'm going to now open up, I think we have a couple of slides actually first. Before we do that, maybe one slide here. So I'm going to just show a function called, and this is maybe the most important function of the day, which is love.graphics.newImage, which takes a path. And so what this allows us to do, so yesterday, recall, we used love.graphics.rectangle, which all that did was draw a rectangle at a particular XY coordinate. So love.graphics.newImage will allow us to load a image file of any kind we want. It supports most image types. PNGs are very common, but you might also have GIFs or JPEGs. And then with that, we'll store that in memory, and then we can draw that onto the screen with love.graphics.draw, which is another function that we'll also take a look at. So I'm going to come back over here to our first example. Switch over to my source code here. You'll notice in the distribution, there's a few existing images that I've placed in there. I've looked at sort of free public domain images to include, but folks could definitely create their own artwork. You just have to use something like Sprite or Photoshop or GIMP, or you could download an image and then just have it in your directory where your main.lua is, and then you can reference it by its file name, by its path. So if we open up main.lua, we'll see in here there's quite a lot of comments, but most of the things that we see in here are actually going to be almost identical, in a lot of ways at least, to what we saw last time at the end of Pong, or even just in the middle of Pong. We have defining our width for our actual screen, our virtual resolution. We have our love.load, which sets our filter to nearest so that things are pixelated instead of being blurry. But we do have here a couple of very important things, love.graphics.newImage. So these are just literally background.png and ground.png, the only two images that we have in our folder here. It's just going to store them in these global variables called background and ground. So with those then, and all the rest of these are essentially the same thing we saw yesterday, just a window setting, setting up our screen, a resize handler. We have our escape to quit the game if we want to. But here, between our push start and push finish call, we have love.graphics.draw, which takes a background which takes rather our background variable. We're going to draw everything. Remember, everything is drawn by its top left coordinate, its top left corner rather. So if we draw the background at 0, 0, it's going to draw it down to the right to fill our window. And then same thing with the ground. Instead of drawing that at the very top though, what we would rather do is we want that to be at the very bottom of the screen. So we're going to say love.graphics.draw ground at 0, so starting at the left side of the screen, but we're going to draw it at the very bottom, virtual height -16, our texture being 16 pixels tall. In fact, in VS Code, I can just show you what these look like really quick. If I click background.png, you see it's this long sort of scrolling texture, which will be very relevant shortly. And then ground.png is an even longer, much shorter texture, which is our ground, and that also will scroll throughout the duration of our code. So if I go ahead and run main.lua here, I'm going to hit Command L. We'll see that we do indeed have something that, admittedly, sort of funnily, is much more impressive looking than, I would say, anything that we did yesterday, but it's very trivial what we've done. It's just a background image and a ground image, and we sort of like already are almost transported somewhere. Now, nothing is moving. There's nothing dynamic happening. It's a rather simple thing. I generally like to go by this style of implementing things in games, sort of sketch out the aesthetics, and then starting to incorporate the dynamism progressively. But we already have sort of the background of our world set up and even the ground set up. But there are, of course, many pieces that remain to be implemented. So let's go ahead and transition here. So the next update that I think is relevant is the parallax update, is what I've titled it. And so parallax is this idea where, and we can see this in the real world if we see like fences and mountains, you know, for example, back to back, or if you're driving down the highway and you look out the side, you can see things move at different speeds. And so parallax essentially is an illusion that we can use to simulate distance or depth in our game. And one of my favorite YouTube channels for exploring illusions in games, just generally speaking, is She Says, and he has a series called Boundary Break. This is a link to his channel. This is a YouTube example, which you can visit this URL to see it. And in Ocarina of Time, which was a game we looked at yesterday, there is a shopkeeper in Hyrule Castle that you can go visit. And if you actually go behind where he's standing, you'll see sort of humorously that the developers, because you can't actually physically move behind him in the game, decided not to model him with legs. So despite the fact that he looks like a real person here greeting you with a rather sort of brusque expression, in fact, he is just a torso without any legs. And this is a common theme, and this is typically how you achieve most things in games that feel like you're living somewhere, whether you're in an open world game and you're streaming all of the surrounding polygons and textures and things in real time. If you were to take a camera outside of your character walking through a world and go far enough away, you'll see that the world is typically not rendered. And most things, if you can avoid it, aren't rendered in the background or off the sides of the screen. It's called culling as well in 2D and 3D. And so this, I think, is an excellent example of that. Highly recommend his channel. He explores a lot of interesting sort of illusion-based camera clipping techniques. Now, in our particular example, we're not doing anything quite that sophisticated, but we are sort of using the fact that we want this infinite world, but we can't necessarily build an infinitely long texture. We do have a long enough texture, and this texture does, if you notice, it has a sort of looping look to it. In fact, here's two images that show the identical part of the screen. This is about 400 some odd pixels in width. And so you can sort of imagine this as being, if you were to almost sort of glue it together and form a ring with it and just kind of spin it around, it would ultimately look like it was infinitely sort of spinning around. And we're going to, infinitely scrolling rather, even as you spin it. And so in order to achieve this sort of infinitely scrollable world, this world that feels like we could just infinitely keep on flying through, assuming we're good enough at the game to do that, then using just a single texture that loops a couple of times, well, we can just achieve that exact aesthetic. Here's a visual illustration of sort of what this might look like. If we envision this is our screen here, and the background is currently at x is equal to 0, but we decide to set some sort of loop point that we figured out by looking at our texture and deciding, okay, this is the pixel at which the exact same, this exact same part is right here, then what we can do is, we can't really model a ring per se very easily, but what we can do is say, okay, once it gets to this loop point, why don't we just set it right back to 0 immediately? And then if it's scrolling, it's going to essentially come back here again, And then once it does that, it's going to hit 0 again, on and on, forever. Imagine that being sort of animated, and you'll see the effect. And this is a technique used in infinite scrolling all throughout 2D games and in 3D games for certain effects for texture scrolling. And this is how we're going to accomplish this sort of infinite, same thing with the ground texture, but this is how we're going to accomplish the idea of an infinitely scrolling world so that we can fly through. So I'm going to go ahead and walk over and let's take a look at bird 1, which will be our next example. So if we open that up, let me go ahead and close these other files. So we keep our textures imported that we did. We're going to use the same textures, but we want to, first of all, scroll them. Now recall last week when we looked at Pong, when we looked at the paddles and the ball, they had a sort of delta y in the case of the paddles, but also the ball had a delta x and a delta y. And it could move around, and we would adjust the x and the y based on this delta x, delta y, the velocity of the ball. And over time, if we multiply by dt, which was our delta time, that ball would just move in whatever that direction is. Essentially, the xy models a vector of direction, and the y just models a vector that's just y-aligned. But also notice that we specified, as I pointed to in the slides, this looping point here at 413. Now, the looping point is the point that I've looked at the texture to decide, okay, that is where the texture is identical at 0 and in this case 413. So once we go over 413 pixels, assuming we're going to scroll the texture towards the left, because if we scroll the texture to the left, we're going to look like we're moving to the right. So if we just keep doing that progressively, and then right as soon as we've gone 413 pixels to the left, we'll just set the position back to 0. It'll almost look like it did a complete in-place movement, and then we just keep that process going infinitely. The way that we do that, the way that we can easily do that, is through a modulo operator. So you'll notice in love.update, we're taking background scroll, and then we're going to do essentially the same operation mathematically that we did to everything in Pong that moved last lecture. We're going to multiply the scroll speed by delta time, add it to whatever our background scroll already is, and the ground scroll, it's the same idea here. But we're going to modulo by the background looping point. And so that's going to, once it hits that 413 pixels where it's really the same exact image, if you were to copy and paste it over, it's going to modulo it back to 0. So this background scroll is going to set back to 0. So recall, modulo is essentially division. It's very similar to division, but instead of giving us the actual divided number, it'll give us whatever is left over. So if we modulo by background looping point, if we're at 413 and we modulo by 413, we'll get back the value of 0, because there's 413 divided by 413 is 1, but there's 0 remainder. So that's what modulo operator does. And in this case, because the ground texture is so similar throughout it and much smaller, we're doing the same thing, but rather than set a looping point, we're just going to set it to the virtual width, and it looks fine. It works completely fine. And here, as you can see, we draw the actual background by its negative background scroll. So we make it shift to the left, and then same thing for the ground scroll. So if we run this, you'll see indeed that we have a sort of parallax effect, because recall, and I'll take a look at the exact numbers in a second, but the background is moving at an actual slower rate than the ground is. The ground is, because it's closer to us as the viewer in this particular shot, that's the way we want to frame it. These mountains are very distant. The slower the things move, the more in the background they're going to be perceived to be. So these mountains are perceived as a background element, and the ground is perceived as an upfront, or as a closer element to the camera. And so we can see that here. If we go up to the scroll speed is actually double. You can adjust this to whatever you want. Essentially, the slower the speed, the farther away it's going to be. If it's a 2 pixels, it's going to look like it's really, really, really far away, for example. But that's essentially what we're doing. We're just doing a double, a halving on the scroll speed of the ground to achieve the mountains looking as if they're, even though they're just literally just textures, they're just pixels being drawn on the screen, they look as if they are, in fact, different depth-wise elements. So we have our background elements now, but I would say probably the most important thing in Flappy Bird is that we are missing our actual bird texture now. So it's a really trivial thing at this point, because we now know how to draw textures onto the screen that we can just draw if we want to, just to get started at least. Let's just draw a bird texture, right? It's just an image like anything else. I'm going to go ahead and open up bird 2. So let's close out bird 1. Now you'll notice that we have a bird.png in this example, and again, these are just images that I might have even made bird.png potentially at one point. I don't actually, it's been a while now, but bird.png, you could just take a file from the internet, you could create your own. Again, it's just a piece of pixel art, but it's in here now, and there's also a bird.lua. So if we go over to our main.lua, we're taking this opportunity as well to reintroduce, remember, classes, object-oriented programming. So if we know we're going to need a bird, if in general we know we're going to need to model some data in some way that we could think of as being real-world entities or the like, I think it's good to start off just already getting the class in place. So in this case, we've created a class called bird, and we're just instantiating it here. We're creating a new bird, and we'll take a look at that in a moment, but we're doing that as a global variable here in a love.load function. And then if we go down here, we're not doing anything really fancy with it yet, but you'll notice that now we have bird::render. And so that's just going to draw our bird. And our bird is going to, if we open it up, actually handle its own graphics. So in this case, we're doing self.image. Recall, these are just a way to refer to whatever the instantiated entity is. And these are just setting fields to it. So self.image, it will hold its own image, and that's going to point to love.graphics.newImage. We could just create new images and all these things anywhere we want to. They're available to us anywhere as long as we're running through Love. So we just load up bird.png. You'll notice that there's a couple of functions here that are pretty useful. So instead of actually hard coding the width and the height and having an idea in advance of what that is, we're creating it dynamically by actually getting the dimensions of the texture, which is something like, I think, 20 by 12-ish. And the benefit of this is that in theory we could just load in whatever texture we want to. It could be some larger or smaller bird, whatever we feel like. But here, if we just do self.image:, this is a method on an image object, one of these new image, whatever this new image function returns. It's going to have a method called getWidth and getHeight, which will be integer values that now we'll set to self.width, self.height. And then we're just going to position it right in the middle of the screen. And we're using virtual width and virtual height divided by 2. We're subtracting half of our width and our height so that it's right in the middle of the screen. And then we're using love.graphics.draw on self.image, self.x, self.y. Quite a bit more readable, I think, than having a ton of magic numbers all over the place, which in general we want to avoid. It will come up periodically, but in general, if you can sort of put things into variables or constants or the like, things tend to be a little bit more readable. And so that's what this bird::render function is doing. It's just deferring essentially to this render function here. So if we run main.lua in bird2, we'll see that it doesn't look very convincing as in terms of the gameplay, but it is functioning properly. We do have our bird. It's being rendered perfectly in the middle of the screen, and the background is continuing to scroll. So we do sort of feel like almost, I guess, we're flying through the sky in some strange form. But yeah.
Syntactically, what's the difference between the colon syntax and the dot notation?
Sure. So syntactically, between the dot and the colon notation, a colon means that we're going to pass an implicit self to this function called render. So tables can be defined. This is sort of the prototypal method of doing object-oriented programming, which Lua does, and JavaScript also does this. But essentially, the bird class has these functions defined within it called render, and then each object, each bird object, or each whatever class, if you wanted to call that render function and then have it automatically know that it's the bird that we want that render to apply to, this colon essentially performs the equivalent of doing this if we were to do bird.render of self. And so that's with the colon. Without the colon, or with the colon, we no longer need to do that, and we can treat every function as just essentially not even needing that argument defined in its definition. As you can see, render here just assumes to not take any arguments, and so it doesn't need to know about self. That's something that Lua takes care of for us. So despite the fact that we now have our bird rendering, we do need to, I think, add a few elements to make sure that the game is believable and also that there's some dynamism at play. So what we're going to do, I'm going to go ahead and close out these examples here. And then the next piece that we need to look at is the gravity update. So gravity in this case is really the element that makes Flappy Bird a game. It is a constant, essentially. We can think of gravity as this value that's pushing down on things to make them fall down, increase their y velocity, to make it more positive over time. It's about 9.8 meters per second squared is the acceleration rate of gravity. And we're going to model something kind of like that numerically. It doesn't really work quite that way because of the way the pipes are of weird size, and who knows how big the bird is in size. But essentially, we can sort of model things if we think of things in those terms. So I'm going to go ahead and open up bird 3. And then if we go to our bird, ultimately that's going to be the, sorry, I didn't mean to open the bird PNG. Our goal is to get our bird, instead of just being static on the screen, we want it to actually fall down, because that's the overall thing we're working towards. Remember, we want to be able to bounce our bird up and down. And the thing that's essentially pushing against us is gravity. That's the main thing we're fighting against. And so we're going to, every time we hit spacebar, we're going to move up. But to start with, we want to get the bird at least moving down towards the ground. So the first thing that we're going to do is we have to know how fast we want to move down, right? So gravity is about 9.8 meters a second squared, and we're just going to arbitrarily kind of go based off of that. So we're going to say we're going to have a constant here of 980. Now you'll notice that I defined this variable using this local word, which we'll start to see more of progressively throughout the rest of the term. But everything so far that we've seen has just been defined without local, just like this. And what that means is that anything throughout the entire application can see that variable. But there are certain situations where you might not want every variable visible across your entire application. If you're using, for example, somewhat simple names for variables, it's higher of a likelihood that you accidentally reuse or overwrite or the like a particular variable between files. So it's generally better practice to avoid globals as much as you can outside of particular circumstances that we'll take a closer look at throughout the remainder of these examples and throughout the rest of the course. But for right now, we're just going to keep gravity local here using the local word, which means that just whatever's in the scope it's defined in has access to it. This scope and any inner scopes, but nothing in other files or anything of a higher scope. And if we come down here, you'll notice that we've set a dy to start with. So our bird is never going to have an x velocity. It's the only way that we're moving, quote unquote, through this game world is actually an illusion. All of it is just the background scrolling, and there will be things that move. The pipes that we saw will move throughout the game space, but all of that is simply an illusion. We're not actually moving through anything. The only direction which we're actually going to have a velocity that matters is our y-axis. And so we're setting it to 0 to start with, so no movement on the x or the y. But you'll notice that we defined an update function in here. And what we're going to do is defer to this update function from our main.lua. We're going to call bird update and pass in dt. But what we do is we just take our delta y, and we're going to add gravity times dt. So over a second's worth of time, our dy will go from 0 to 980, which if 100 pixels was a meter, that would be about 9.8 meters of distance that we move or we accelerate through every second. And then not only do we have to do that dy operation, we also have to add the dy to our actual y value, our coordinate inside of the bird object, because that's what we use to render the bird. And so if that never actually gets updated, the bird's dy might change, but it won't actually update visually. So we're going to do that. We're going to then take that dy and we're going to add it to our y, also multiplying by dt. And then we're going to draw just the same as we did previously. And assuming that main.lua has in our update function, we'll just go ahead and go straight to there. Notice that we added bird update and we passed in dt so that it would have access to that. We can then run this. And we'll know it's kind of hard to see. It's very easy to miss. But let me run it one more time. If you pay real close attention, you'll see that it just falls right down through the ground, which is the exact intended effect for our game. So we have an initial initial 0 value of our y velocity. That's going to add every 1/60th of a second. It's going to not only get faster in terms of how much it moves, but it's also going to just keep adding that every second until we just fall straight down through the Earth. There's no collision or anything. Nothing is testing for these things. Once it goes out of bounds, we don't see it. It is actually technically still increasing and moving, but it is, for all intents and purposes, out of sight, sort of out of mind. So it is a little bit underwhelming currently that our bird, all it does is just essentially fall through the floor, which is not exactly what we want. But this gives us the perfect segue into actually being able to correct for that with input, meaning that we can press spacebar or tap on the phone or the like to actually make the bird sort of jump up and start to fight against gravity, and then we'll have the beginning of our sort of interactive gameplay loop, so to speak. So I'm going to go ahead and transition to the slides here. In order to do that, we want to do or move on to what I call the anti-gravity update, so just kind of cutely naming it. But essentially what this means is the way that Flappy Bird works is that, and this is a sort of complicated graph seemingly to describe, but overall I believe this was usually used for a neural net sort of training a dynamic thousands of Flappy Birds moving around the screen and calculating optimal play paths for them. But you can see essentially all the elements that we are going to be looking at throughout the game, throughout the rest of the game examples, are shown here visually. We have the size and we have the gravity vector here, which is modeled essentially with the 980 pixels that's per second that's applying to our y, our actual y velocity positively. But there's another important aspect, which is there's a jump velocity. And this jump velocity is what we're going to look at with the anti-gravity update. So what we can do, essentially, even if we have this gravity pulling us down constantly, if we essentially just sort of say, okay, well, we're getting higher and higher in terms of our dy per second, but we can just hard set it negative, the opposite of a positive y velocity is going to be going negative, which means we'll just go up towards the top of the screen. And the effect this is going to have is that we essentially, rather than just do a continuous updating of our velocity, minusing by some delta time amount per frame, we can just hard say, hey, let's just set it to like a high negative value, and it will immediately start going up really fast. But because we're always applying gravity per frame rather, it's going to immediately start to correct for that. And that's what's going to give us this appearance of sort of jumping. We go up really fast, but really within a very short span of time, gravity's already doing its thing again, and we're moving back down the screen. And tweaking those values, tweaking gravity, tweaking the jump velocity, so to speak, are really what's going to be behind balancing this particular game specifically. In addition to, for example, the pipe speed as they move through, and also the gap between the pipes. Those would all be like the balancing variables that you would use if you wanted to tweak how hard or easy your game is. Right now it might be a little bit too hard. We could certainly tweak a couple of these variables and see if that makes it easier to play towards the end of the lecture. But you can see, as a preview, we also have our pipe separation, our pipe gap. These things are also what we're going to be taking a look at in some examples to follow. So we're going to go ahead and transition now to Bird 4. So if you go ahead and close these out. Now if we move over to here, so we have our Bird module. And this is all really going to stay the same. What we want is in our bird.lua, the key is, we will take a look back at main.lua in just a second because there is a very important thing here we need to talk about. But the main thing here that's doing the work of this anti-gravity update, so to speak, is, again, we press spacebar. We want that spacebar to give us this jump up. And to do that, rather than have a continuous sort of like decreasing of our velocity, which is make us go up really slowly, we're going to hard set our velocity really high in the negative direction and then allow gravity to correct for that. And so that's what we're doing right here. We just set it to a burst at negative 300, which is within about a third of a second, that's going to be brought to 0 from gravity because it's going at 980 pixels per second. And then it's going to immediately start applying that 9.8 meters per second squared down in the y positive direction once that has been reset back to 0. And so again, you can tweak these values a little bit depending on what you want, but we're just hard setting the dy to negative 300 and then allowing gravity to do its work. Now you'll notice that I have a function here called love.keyboard.wasPressed. And what that function is actually not a function that's inside of love. This is a function that we have chosen to define ourselves because Lua is dynamic. You can essentially add functions to whatever you want to. And the unfortunate thing is that in love, most of those callbacks that we all saw should and can only be defined in one place, namely your main.lua. If you want, for example, when we looked at continuous input for the paddles, it was love.keyboard.isDown, recall, and we can pass a key in like A or W or up or down. And that'll just give us a Boolean, hey, are we pressing that key actively? Yes, no. But what if we want to just have like an instant click? Well, or an instant key press. Well, the only way that we've known to do that so far has been through our actual love.keyPressed callback function in main.lua. But we can't just define that in here and check for that. What we want to do is we want to say, we could, you could have ways where you could define something like that, but then we're going to have to say, okay, we're going to manipulate the bird's dy, bird.dy equals -300, and we're sort of getting our hands dirty with the objects themselves. But if we want to encapsulate this behavior and let the bird manage its own input handling, and let anything manage its own anything, we need sort of ways to cleverly get around main.lua's predefined callbacks. So if we go to main.lua again, we'll notice that we have a little table here that we've defined called love.keyboard.keysPressed. We're just defining it to an empty table to start with. This is in our load function. So right at the very beginning, at love.load, we're just going to create this. And again, we're just extending this. We're just adding this to the love.keyboard namespace, the love.keyboard module. We can just add whatever we want to it. Love.keyboard is a thing, but love.keysPressed is not a thing. So we're just going to say love.keyboard.keysPressed equals an empty table. And then inside of our callback function, notice that we've added this in here. This was in here previously, but we've gone ahead and we've added love.keyboard.keysPressed key gets true, which is this table that we have just defined up in our love.load. So what that allows us to do is basically keep track per frame. Oh, okay, I pressed this key, and then now we can just globally have access. Okay, which keys got pressed this particular frame? If we just look at whatever key is in there, we'll know, okay, oh, I pressed A this frame. Love.keyboard.keysPressed at A is true, and everything else will be false, assuming that we initialized it to nothing, or it'll be nil rather, and then we can just set it all to be nil later, or we can set it to a fresh table. If we go down here, we see the definition for that function I alluded to, love.keyboard.wasPressedKey. This is our own function. We're just extending love.keyboard, and we're just doing a check on that table. If love.keyboard.keysPressed at key, meaning if there's a value in there at all, any truthy value, then return true or return false. And so what that lets us do is we can just call this now anywhere we want to. Love.keyPressed will continue to fire. It'll populate this table. And then anything throughout the entirety of our code can just use this function to see, oh, was it pressed once? Not love.keyboard.isDown, are we pressing it continuously, but did we just press it once? The important thing that lets this work per frame and actually apply to individual frames separately is that at the end of update, we need to reinitialize keys pressed, that table, to be an empty table, so that everything is essentially emptied out, so that there is no memory of whatever we pressed this frame on the next frame. Everything's a blank slate, and then per frame we just populate with whatever we trigger in our key pressed handler. So if we look back at the bird.lua file, we see here love.keyboard.wasPressed. That's our own function. Love.keyPressed, if we press spacebar, it'll handle that for us. It will put it in that table, it'll mark it as, yep, you pressed it, and then we can immediately just check in our update function, anything that checks with an update, which is what this bird::update is being called right here, it will check that table with that function and then return true, and then we can just process individual keystrokes as if we were essentially doing it in our main.lua, but now we can do it in any class and any file that we want to. Normally this would not be possible, but we have extended effectively our ability to do that. So I'm going to go ahead and run this example. And we'll see, I have to remember to actually start pressing spacebar. But now, anytime I press spacebar, you'll notice I am indeed going up about at a velocity of -300. Gravity is pushing that down. But if I don't press anything, it'll start to accelerate down more and more. But I can just immediately shoot up -300 pixels. dy, gravity will subtract that. And then within about a third of a second, it's already sort of zeroed out. And that's how we have the sort of convincing input loop of Flappy Bird, so to speak. Yeah.
Is love.keyboard.keysPressed a table that comes with the Love API, or is that something you added?
No, this is something that we are choosing to add ourselves. So everything in Lua is dynamic. Tables are all dynamic. You can just add everything. At the end of the day is going to be a table of some kind. And so you can just add whatever key you want and put in whatever value you want. In this case, love.keyboard comes predefined, but it does not have a keys pressed table. It also does not have a love.keyboard.wasPressed function. We are also adding our own function to it as well. Okay, so that is the anti-gravity update. So now we have essentially a model of how to fight gravity and how to get our input to work properly. But now, it begs the question, how do we actually start to get the obstacles in our code that allows us to have something to dodge with our bird? Because it's not really, right now there's not really much of a game there. You can move around, you can jump around, but the pipe is kind of the ultimately, it's even shown on the slide, it's kind of like the missing piece. So the next update, the next piece of code is going to be called the infinite pipe update rather. So why don't we go ahead and open up that example. So I'm just going to go ahead and close out these examples. Open up bird 5. You'll notice we added a couple of things here inside of this example. So we have a pipe.png. Again, just an image. It's quite a tall image, but this allows us to render it even potentially really high up on the screen, and it'll still fully show. You could, in theory, loop segments of the inner part, and that would function just fine too, but we just found a tall graphic that we're going to use. And we also have a pipe.lua. So in our main.lua, let me go ahead and kind of come down here. We're requiring pipe. We have a table that we've added, so local pipes gets empty table. So this is essentially just going to function as an array for folks familiar. And tables can function just like arrays in languages like C or C++ or Java. The table is Lua's sort of catch-all data structure for anything that requires multiple things. And so we're going to store a bunch of pipes in this table, and we're going to scroll them, and we're going to move them throughout the screen. And so what we're going to do then, last time, up till this point, we haven't really had a collection of multiple of the same things. We've had 2 paddles, we've had a ball, and then we've had our bird, but we haven't had, like, if we need infinite pipes, we need a way to have, some data structure that can store. I'm not going to define pipe 1, pipe 2, pipe 3, pipe 4. I'm going to put them in a table or an array of sorts. So we're going to go down here and just take a look at our update. You'll notice that we added a timer. So this is just a very simple timer. And actually, we might have defined that up here at 0. So what this is going to do is going to add, essentially what we want to do is we want to spawn a pipe every so often, like maybe every second or two, in order to account for the fact that we've spawned or that we need to spawn a pipe. Well, we know from love.update that dt field that it passes in is just a time, it's a fractional time in seconds. It'll be some like 0.016, or depending on what frame you're running, it might be higher or lower than that. And so if we just keep adding that fractional value to some variable, in this case we started at 0, but once this gets to 1, we'll know that a whole second's worth of time has passed. Or 2, we'll know that 2 seconds worth of time has passed. So through using a timer and adding dt just over time to it and doing a conditional check, we'll know, okay, a second's passed, 2 seconds passed. I want a pipe to spawn every 2.5 seconds or every 5 seconds. This is how you do that. You just keep adding dt to some value and then do a check on it. So if we go back down a little bit, we'll see every update we're going to, just by default, we're going to start by just adding dt no matter what. And then we're going to do a check here. So in this case, if spawn timer is greater than 2, meaning at least 2 seconds have passed or more than 2 seconds have passed, you'll notice that we're using this function called table.insert. This is a function that's in Lua. This isn't a love thing. This is how in Lua you add to a table. You say, okay, table.insert is table isn't a variable in this case. It's actually a keyword. Table.insert into pipes. Pipes is the name of our table that we defined way up at the top, recall. And then we're going to just instantiate an empty pipe here, which is what this constructor is doing here. Recall, this is the class constructor syntax from our last lecture's example. and even up above with the way that bird is defined. So we're going to create a new pipe, no parameters. We'll take a look at the pipe class in just a moment. And then we also reset spawn timer back to 0 so that now we'll begin retesting, or we'll begin to reaccrue that 2 seconds worth of time before the next pipe gets spawned. Now, another important detail is that, okay, well, we can populate that table all we want to, but of course those pipes are going to have to move, and moving, as we know, requires updating. It requires some operation on DT, delta time, and we can do that inside this iteration here. So this is using a for loop in Lua. This is how you do for loops. So there are a few different ways to do for loops. This is doing an iterative, it's using an iterator. So what it's doing is it's saying for k colon pipe, and these are variables that we're choosing. So you can say for something comma something, meaning for every key value pair in this table. So everything in a table is a key value pair. By default, if you use a table, as you can see here, we're just doing an insert. So we're just saying, okay, sequentially into the table, let's just add an element, add an element, add an element. It's going to treat it much like an array in C or C++ or Java, where at index 1, as we'll find out, not 0, one of the quirks of Lua is that it is not 0 index, which folks who have taken another course might know that arrays are typically 0 indexed. In Lua, tables are 1 index, so we'll start at index 1, there will be a pipe, then at index 2 there will be a pipe, then at index 3 there will be a pipe, if we just do this over and over and over again. So when we call this iterator here for k pipe, this just means for 1 pipe, for 2 pipe, for 3 pipe. It's key value pairs. So the key is the index, and then the value is going to be what's actually stored in that table at that index. So at index 1, it's going to be a new pipe. At index 2, it's going to be a new pipe. At index 3, it's going to be a new pipe. But Lua, in addition to storing numerical indices, allows us to store strings and have those be our keys. And so we can say, you know, for example, as we'll see coming up pretty soon, if we want to have a bunch of sounds, which we even saw last lecture, and we want at the particular sound for like a crash, you could say at index crash, store this audio source. Well, that's going to be not a numerical index anymore. Now that's going to be a string index. So if we were to do that same thing, it would be for k pipe would be, or for k sound rather, it would be for crash would be the key, and then pipe would be the sound, or sound would be the sound. So this is just a way of iterating over a table to get the keys and the values. We don't really care about the keys necessarily. Well, actually we do, because we want to remove them, and that's how you remove elements from tables. But in particular, often you'll want to just use pipe. You'll just want to often use the values if you want to perform some operation off of those values in your table. So this is how we iterate over an entire table and get back each individual pipe. And then from there, we can then now call pipe colon update on DT. And you'll notice that the other key piece to this iteration is that there's this pairs function. And that's a function that's in Lua. So pairs is essentially just what gives us this ability to iterate with key value pairs. Literally, the name is pairs in the function to give us that ability. So for every k pipe in the pairs of pipes, we're going to update pipe with DT. And then we're going to do the check here. If the pipe.x, so this is where we're going to be able to actually remove, we could just do this and let this run forever. We could just keep adding pipes every 2 seconds and just like store it and it's fine and let it run. But if we did that every 2 seconds, we're adding a pipe to this data structure in memory, and it's just going to keep getting bigger and bigger and bigger. And it's also going to mean that this iteration is going to take longer and longer and be more processing. So if the pipe gets past the edge of the screen, if it's less than the pipe.width, I think this needs to be, if pipe.x is less than, sorry, this might be a typo. If pipe.x is less than 0, then we're going to table.remove. This is another function. So table.remove is a function that will actually, again, just like up here where we had table.insert, this is another Lua function to remove from a table. We'll say table.remove at pipes will remove k. And so what that's going to do is, again, k pipe. So remove requires that you give it the key that it wants to remove. So it's going to take a look at the collection that you give it, the table that you give it. It's going to say, okay, what key do you want me to remove from the table? So the table is pipes. The key is k, which is why we call it k. And then so if pipe.x is less than 0, or less than or equal to, or actually no, it needs to be less than, okay, I realize now why it was set to that, because it has to be, because it's drawing on based on its x-axis, its x coordinate rather. Once that gets to 0, it's still going to be visible on the left edge of the screen, so we want it to actually be equal to the negative size of the pipe. That'll be the moment that it just goes past the edge. If it's like, if the pipe's 30 pixels wide and it goes to past the left edge of the screen, 30 pixels, it'll just be at the point where we no longer see it, and so that is why we want it to be less than pipe.width. And so if it's at that point, just off screen, we're going to remove it from pipes. We're going to remove that key from pipes, and then that way, no matter how many pipes we add to this collection over time, we're not going to be just getting this bigger and bigger structure. We're adding pipes, and we'll maybe get like 5 or 6 on the screen or so. They'll be moving, but then eventually, once they get just off screen, the first one, the earliest one in the collection will disappear. And so then we'll have 4. And then maybe the 5th one will get added, but then the next one will have moved over here, and now it just gets removed. And so we'll see the actual operation of moving if we go into pipe here. Oh, sorry, I thought that was the Lua file. We'll go into pipe.lua, which this is going to be quite a simple definition here. You can see we have a constant defining the image, the actual image here. We have its scroll speed. We're just defining negative 60 pixels per second approximately. But you can see that we want to start with the X actually all the way off screen. We're going to start with the pipe being off screen. Remember, they're going to scroll in from the right-hand side, and so we're going to start it just off screen by setting it to virtual width. And then in update, we're just going to do a very simple, we've seen this a bunch of times already, times the pipe scroll by delta time. And then over time, this is going to essentially set the, it's going to keep it scrolling until just eventually, again, once it hits negative its width off screen, it's going to just be, the cleanup function is going to call in main and it's going to disappear. But also, for fun, part of the procedural generation aspect of things and the sort of variability of the way the game plays and also looks, we want to randomize the y-axis. Recall that we did this last lecture where we set math.randomSeed with os.time and in the love.load. So that gives math.random this always fresh way of randomizing. And we're just going to decide to draw its y value between the middle and the bottom of the screen-ish, approximately. A little bit above the bottom of the screen, virtual height minus 10. But you can see here we say a range between virtual height divided by 2, middle of the screen, and then virtual height minus 10. So every pipe will randomly be tall a certain amount, but they'll always be moving and eventually getting off screen, and they'll always start at the right edge of the screen. So that was a long explanation. Let me go ahead and just run this example so we can see it. And I can even, I think, press spacebar, can I? Barely. You'll see that these couple are a little bit low, but they all are random. So we have some that are just spawning even slightly off screen there. You got one that's actually almost made it halfway. But you can see on the right edge of the screen, we have they're actually starting, they're spawning. And then every frame, that scroll speed, which is negative 60, so about 60 pixels per second, they're just moving right to left. Once the oldest one hits there might be a missing, or maybe there's a gap there actually. Either that or they're just slightly rendering off screen. But the actual pipe will be taken out of the table.remove at that index. And so we just have this infinitely drawn landscape now of pipes. So we sort of are achieving the aesthetic of what we're going for. Now, there's things missing. Obviously, the one thing is that we're just, I can just bounce through these. I can just float through these pipes, and it's fine. We're not actually doing any collision detection. A slightly subtle thing that people might be noticing is that the pipes are actually slightly shifting to the last pipe, or the first pipe is shifting slightly to the right on every time that the pipe to its left goes off screen. And that's because when you remove something in the middle of an iteration, the table is going to essentially skip the next index. So we're going to fix that, and we'll take a closer look at that in a second. So that's a bug. And also, there isn't a pipe above this pipe. On each of these pipes. And so we need to model a pipe pair is what we're going to call it. And then so we need to model collision first off. We need to fix the way that we're removing pipes from our table. And then we need to also add this second pipe on top of all of these. And then once we have those pieces in place, really that's essentially the core of the game. Yeah.
when you call table.remove to remove a pipe once it's off screen, does Lua then also garbage collect the memory, so to speak, so that you're not just accumulating more and more objects somewhere in memory?
Yes. So anytime that you set a key to nil or you remove a key from a table, Lua's garbage collector will eventually clean up that memory. It is a garbage collected runtime, so it's not something that you have direct control over, but just like JavaScript or Python and any of these other scripted languages, it'll do garbage collection behind the scenes when things are no longer referenceable or keys and tables are removed. So that was infinite pipes in a nutshell, and we do have some more work to do to get us to the sort of full Flappy Bird sort of aesthetic. And so that brings us to Bird 6, which is the pipe pair update. This might be one of the more interesting and important aspects of this particular repo, because that's what ultimately determines the game itself overall. The game would be pretty easy to play if all you had to do was jump over pipes, probably. And so what the designer of the game did was you have pipes that are sort of above and below each other, sort of oppositely oriented, but with a space between them that's kind of just small enough to get through with practice. And so we can look at, this is again another sort of example of an illusion where, you know, in real life, you know, you might see pipes that are built into the ground in this sort of way, and it makes sense, but certainly not just floating from the ceiling, from the sky, and not connected to anything. But because they're rendered off screen and they're tall enough, we don't ever really see anything to suggest that they're not part of the world in some way. And so we give people the illusion of these pipe pairs that exist in the world that we're navigating through. Now, every pipe pair sort of has its own you can think of it as its own new object. So these pipes so far, every object that we've dealt with has an X and a Y value. We're going to think of these pipe pairs as having their own X, Y at the top, and then they're also going to have a gap size in the middle here, sort of this size between the pipes. They'll also have a gap between them, their spawn interval, so that, you know, the more pipes that you have and the faster sort of the slope of your pipes as they get generated, the harder your game might be. If you don't have very many pipes that generate and the slope between them is relatively gentle, it might not be as hard as, you know, maybe you have relatively sharper differences between the gaps and they're more frequent. And so that's another example of ways that you can balance your game, which we saw back a few slides ago. And then we can look at this area. I've sort of named them the dead zone and the spawn zone, which is kind of ultimately what I talked about in the last slide a little bit as I was looking over the code. But this area just means essentially where things get deallocated, where the table will actually get cleared of pipes as they move past the edge of the screen. And then the spawn zone is just where they start and they move in from right to left. And this is just a graphic to sort of illustrate that idea. So we're going to explore that now with some code. If we move over to here, I'm going to close out the examples that were up here in Bird 5. We'll open up Bird 6. And you'll notice that we now have a pipe pair.lua class here. So I'm going to open up main.lua. We'll come down here just a little bit. So instead of pipes, now we have pipe pairs. So the idea of a pipe pair, ultimately folks can model a lot of these things however they want to, but in my mind, because they move together, I sort of envision these pipe pairs literally as an entity, even though it's comprised of two entities. But that's the benefit of object-oriented programming, or just like more, I guess, modeled programming. You can have things that are relatively complicated and intricate, have multiple pieces nested within them, and hide the details of how they work so that you can just think in terms of these high-level concepts. So instead of pipes, we now have pipe pairs, and this will actually hold within it two separate pipes that we can use to do collision detection and move around and angle and orient and things of that nature. We're going to keep a last Y for the gap placement, so that one of the bigger issues that you could have if you were to go purely random with the way that you organize the generation for these pipes is that they'll just be all over the place. They'll be very staggered and crooked, and it'll be pretty much impossible to play the game no matter how good you are. So if we keep a record of our last Y, then we can just simply adjust whatever that value is by just adding or subtracting some small amount from it. And then what that'll do is it'll ensure that we sort of like move in a gradation. It'll look like it's smooth and intended, which is the way that the original game was implemented. And so if we go down to a few functions down to our update, we'll see that rather than spawning a pipe and adding it to our table, we now spawn a pipe pair. It takes a y value, so that y is going to ultimately be determined by this last y, and that's where this essentially gets calculated based on the last y plus some random value, which will allow it to move sort of gradually throughout our game space and not end up being, if it's too random, it'll just be impossible to play. We want to ensure that we keep it sort of graded. And then otherwise, it's largely the same. We're doing another iteration here for every k pair in pairs of pipe pairs, which the syntax we saw last time. We're just going to update the pair itself now, not the pipes, which the pair, as we'll see, defers to updating the pipes. And then we have our remove step actually separate. Previously, if you recall, we had the remove step inside the update stage, but there's a problem with that because if we actually remove anything from a table while we're iterating over it, that can cause issues because we will essentially, on the next iteration of our loop, if we're going sequentially, if we remove index 2, let's say we're iterating through our table and we remove index 2, the way that Lua actually deals with removals is that all of those indices get shifted back by 1. So if you have, let's say you have 3 pipes, you delete pipe 2, then as soon as you delete pipe 2 becomes what was pipe 3, and pipe 3 is now nil. Nil is Lua's way to say nothing, and so you effectively would skip over that pipe, whatever pipe would have been there. If you had 5 pipes and you delete pipe 2, it would essentially become 4 pipes in width, but pipe 3 would take 2's place, pipe 4 would take 3's place, pipe 5 would take 4's place, and you would skip over iterating over pipe 3 effectively by deleting 2 and having 3 get shifted into 2's place. So typically, anytime you want to do a removal from a table, you either want to do it in this way where we are updating and then removing afterwards. And we do that with this flag here, pair.remove. That's what we trigger that in pair update. So we basically say, okay, this pair should get removed. Then we have a cleanup loop. Or you could also iterate from the end of your table to the front and then delete things. And then because things get shifted from the later end of the table to the front, deletions won't actually impact further iterations because your iteration will have gone to, you'll be decrementing instead of incrementing. But we're choosing to do this other approach here, which is going to just kind of also explicitly show us that we are separating the removal from the update. And there are certain situations where you might want to keep things alive for a little bit for other things to update and affect things and maybe not do a removal right away in place. You might want to flag something so that other things can do something to it before it gets removed right away. And so also, in our pipe pairs, or in our draw function, we're iterating over all of our pairs, and then we're just pair rendering instead of pipe rendering for every pipe. So let's go ahead and open up pipe pair.lua. We'll see here that we're taking an approach, and I previously alluded to tables, the difference between having tables that are incremental in that they get automatic numbered indices like 1, 2, 3, 4, and again they all start at 1 in Lua instead of 0 in case that ever causes confusion. But you can also have tables that are defined with strings, and we did this last week or last lecture with sounds, and we're going to do that again with sounds in this lecture example, but also we can just do it with anything we want to. In this particular case, if we think about a pipe pair, we know that we want a pipe on the bottom, the exact sort of situation that we already just looked at, where every pipe is a sort of bottom pipe in our world, but we also want a pipe that's above that pipe, and that's creating a gap between the two. And so to do that, we're just going to say, okay, a pipe pair has its own self.pipes table. This is just another table, which has 2 keys, upper and lower. And so pipe, we've changed a little bit now. So previously, remember, we just had an empty set of parentheses for pipe. It didn't do anything. It didn't have anything. It was just all essentially randomly decided where it lived, what its position was. But now it takes a string as its first key, top or bottom. This will be important when it gets rendered in a second, as we'll see. The top pipes, if you recall visually, the top pipe and the bottom pipe aren't the exact texture that aren't the exact same texture that's being rendered. If you can even switch to the slide here and you can see it, the pipe on the bottom is properly being just printed, just drawn to the screen the way that the actual art is displayed, but the top pipe is actually getting flipped upside down. And so that's where it gives it that sort of nice symmetry. But in order for that to actually get rendered properly or to be accounted for, we need some piece of data that's capable of representing that. And so we're going to pass in this string for our upper pipe is going to have this string passed to pipe called top, and then the lower one, you could also maybe put these as top and bottom if you wanted to for consistency. But in this case, we're just deciding to say the upper pipe and the lower pipe has a top-oriented pipe and a bottom-oriented pipe. And then you'll notice that they also take in a Y parameter, and that's the only really important thing that needs to be explicitly placed, because recall, X is decided for us. They're just going to move rather right to left, and that's going to be taken care of for us. We don't need to manage X at all. We don't need to set it. It just always starts at the right edge of the screen, moves all the way to the 0, or it's actually 0 minus pipe width, and then it gets garbage collected effectively. But we do want to set the Y value for these, because remember, we are setting the Y. We're deciding, okay, I want the Y to always be such that the gap never is too far apart from the last gap. We're going to keep track of whatever the last Y was that we set for that, and we're just going to shift the position by 20 pixels or so. And so that's why we're passing these values into here. And here's the remove flag that we set. We set the X already automatically to a little bit past the edge of the screen, virtual width plus 32. We could also set this to virtual width, and that would probably work as well, but I elected to just put it slightly past the edge of the screen. You could also tweak this to your liking, and that would effectively influence maybe the gap between your pipes, which we'll take a look at later. But then you have the update function here. And so now notice that we are deferring the updating of those pipes to this function. This function will actually, it will actually take care of passing a call to both those pipes to render them, so that we don't have to think of them from the main.lua. Main.lua just calls update and render here, and this manages, it sort of wraps over the data of both pipes. And so we just call self.pipes at index lower .x equals self.x. Well, first off, we do the classic delta time multiplication onto pipe speed, and then we subtract that from self.x. So we're always moving right to left by sort of that pipe speed by delta time. And then we're just going to take this pipe pair has its own xy value, and we're just going to pass the x value in particular to the pipes so that they move, so that when they draw, they'll always be moving, but they're being managed and they're being sort of held in this container of information. And so if our x is still greater than negative pipe width, which would be past the right edge of the screen, then we'll do that. But if it's gotten past that point, just like with the other pipes, we're going to set our remove flag to true. And recall, that's what we checked in main to actually do the removal right here. If pair.remove, then just remove pipe pairs from our sort of global set of data in main. And so let's take a look then real quickly at pipe, which has a couple of changes. So most of these are all the same, except we do have this orientation field now, and that was the first string field that we passed into the pipe constructor when we were looking at it in here, this top and bottom. So this orientation is going to essentially flag this pipe and say, okay, am I a normally rendered pipe? Am I just going to draw the texture as is, or do I need to flip the texture for this pipe? And so if it's a top pipe, it needs to flip, but if it's bottom, it just needs to render as is. And so we take that in. Notice here it's the first argument to the constructor. Again, the constructor is the init function with the class library that we're using. And then it takes in a y, and so self.y gets y, it just gets set here. Self.x is equal to virtual width, that's fine. And then if we're not doing any actual updating in pipe anymore, but we are rendering pipe still. We're essentially using a render function in here that pipe pair can just easily call and defer to. So the more you can sort of do things like that and sort of reduce your syntax, look how clean and elegant sort of this looks at a high level. If you're looking at pipe pair and just want to figure out how pipe pair works, you can sort of bury the messier details deeper into your data so that you can think more high level. But we're essentially just drawing the image for the pipe. We're drawing it at X always, but the interesting thing here is that we're going to do a check on our orientation to determine the way that we flip, whether we should flip our pipe. And the way that we do that, interestingly, in Love 2D and in a lot of graphics contexts, is we're going to apply a negative scale factor. And so this might look like a lot of details here. I'll go ahead and just kind of individually new line these maybe for illustration. But essentially what this is try to put this here, so these are all on their own line. we have our, and all of this is nicely documented too on the Love 2D wiki, where they go into detail on all these parameters. But you have the image, the X, so this is the Y. So if it's a top, then we're going to essentially, remember, we're in our pipe pairs, we're rendering both of the, we're rendering both pipes. So what we want to do is, the interesting thing about scale factors is that they will flip something based on the XY coordinate of whatever is being flipped or scaled. So by default, everything that has a normal scale factor of 1 is going to just render down and to the right. So if you're rendering the bottom texture, for example, it's going to render just fine. It's going to render based off its top left coordinate, which is going to, it might be visible from that perspective, or left, sorry, camera is flipping my thinking. But you're going to render from the top left, and then you're going to render down to the bottom right. But if we want to set a negative scale factor, the weird thing about that is that essentially we're going to, if we by default just assume the same orientation of top left, then a negative scale factor on the y-axis means that this upper pipe is going to look as if it is drawing upwards. It's going to flip, it's going to mirror its y-axis starting at its top, and that's going to not be what we want. That's going to essentially greatly magnify the pipe gap distance. So what we want to do is, even though we're going to do this flip operation, so imagine this is our pipe normally, if we were to negative scale factor, it's going to flip it vertically, and we don't want that. We want it to essentially do a flip, but we want it to stay in place. And so to do that, we're doing this sort of essentially adding our height to the y value when we draw it. And so the result of that is that, and this is just when we're drawing it, we're not actually changing its data y value or anything. So collision will still work just fine, but we're essentially offsetting such that we draw the y down a pipe's height worth. So even though we're flipping, even though we flip the pipe vertically, we end up actually shifting it down by that exact same amount, and that has the intended effect of just in place vertically flipping, whereas previously we would have essentially looked as if we mirrored the pipe directly on top of the existing, where the existing pipe would have drawn, and created a tremendous gap. And so that's what this is ultimately doing. We're using that ternary syntax that we talked about last time. If we're in top orientation, then we're going to draw at our self.y plus pipe height, or just our regular y value. And then this is a rotation value here, which we're just going to set to 0. We don't want to rotate. A 1 for our x scale factor. We don't want any flipping. We don't want any scaling on the x-axis. So just a 1 scale factor, which will do nothing on the x-axis. But again, another ternary here. If our orientation is top, then we want to set a -1 scale factor, which will flip it vertically, or just 1, which will keep it drawing top to bottom. So I'm going to undo some of these little changes here, and then save that. And then if we run that really quickly, we will see that we do indeed have pipes that are drawing correctly. So even though we are flipping those top pipes, there's a gap of whatever this is that the bird is going through right now. It looks like maybe 60 or 50 pixels or so, maybe a little bit more. The pipe is being drawn above that, and if we were flipping this, if we were to flip the axis without shifting its height, it will just completely be invisible. We can see that if we were to go here, and instead of adding, if we go into the pipe, if it's a top orientation, let's just do self.y here as normal. We'll see, we will not see the top pipe because it's going to be rendered really high up and flipped vertically. So let's go ahead and just do this. Once the pipes start coming through, you'll see we see no pipes. Even though they're there, the pipes are there, but the way that the rendering is flipping them vertically, even though the rectangles, sort of the collision boxes you can still envision are there, the actual graphic is flipped at the top where its XY is at 0, which is really high up. And so we want to offset that. That's why we go ahead and if I go back into pipe, add that height back to essentially like sort of spoof as if we aren't doing a rotation based off of the XY. We're just doing it based off of we're essentially emulating a center rotation about its midpoint. And so that's what we get here. Run it one more time. We'll see the pipes properly rendering. So anytime you do a rotation, if you want to, or not a rotation, but a scale, a negative scale in one direction, you're going to want to offset things visually if you want it to render in place, a rotation in place, or rather a flip in place. Or you can optionally set the origin point to the center, but that adds a lot more complication with actually setting up and rendering things and just also calculating collision in other ways. So we elect to do, instead of doing a center origin point for everything, we just instead set the, we keep everything based on the XY coordinate, but we just offset the visual. It also helps that we're only doing a Y flip. We're not doing an X flip, which would be more complicated. But since we're just literally flipping in place, or just flipping the thing vertically, we can just shift it down and it functions completely normal as we want it to. So with that, we've tackled what might be the most tricky part of the code. Certainly a lot of things in there, a lot of tables, which are sort of a new way of looking at things, and there are functions that are built into those. And the pipe pair itself is a little bit of an odd data structure on its surface, and it has sort of multiple objects that it's managing now. But thankfully, the rest of the topics we look at should be a little bit less intense. And the next thing that we're going to look at is actually sort of a callback to last lecture, which is this is the collision update. And so remember last week, or last lecture, I had alluded to the fact that AABB is quite a prevalent theme throughout the rest of this course, and in 2D games it's a very common algorithm for doing collision detection. And thankfully everything that we're dealing with today is all rectangular. Even the bird, sort of, even though it doesn't look quite rectangular, we can think of it rectangularly. So I'm going to go ahead and transition over to bird 7 here and just close a few of these. And so most of what we need to look at for collision detection in this example is we just have a collides function. It takes in a pipe as an argument. So what we want to do is we want, essentially as the bird is moving throughout this landscape of pipes that we're creating, these pairs, we just want to check for every pipe pair, is it colliding with either the top or the bottom pipe? Recall each pipe pair, it has two pipes, two rectangles that we need to check for. And so we can do that by essentially, even though this looks a little bit more convoluted maybe than last time, this is the same algorithm. We're just checking to see if there are no gaps at all throughout all four sides of the bird versus the pipes. Same code as last time. The only difference is that we are checking on a slightly smaller rectangle than the bird's actual box. By offsetting based on which edge we're checking, we're just going to either check whether it's the self.x plus 2 or the self.width minus 4 instead of self.x and self.width. And the result of this is that effectively we have a 2 pixel smaller box around the entire bird that we're checking instead of the bird's actual full collision box. And this is a common thing that you'll see game designers doing just to try to overall make their games not feel as unfair. Because if your game is just gives you just a slight amount of leeway, particular in like shoot 'em up games for like old arcade games, like scrolling shooters like 1942, you want to have just a little bit of wiggle room to navigate projectiles and the like. If things are actually hard set to your collision box, then it can sort of feel like, oh wow, that shouldn't, even though by the literally by the standards of the algorithm, it's purely fair. The way that sprites are modeled, sometimes with slightly transparent pixels and just weird shapes and circular shapes and whatnot, it can feel better sometimes to just clamp your, or to reduce your box just a little bit against the things that you're colliding against and projectiles and things of that nature. So that's the main function that does the work. It's essentially the same function that we looked at last week, which was split in two. This one's just all in one condition. We're going to go ahead and look at the in main.lua in our update. We'll notice that we're going to do the update step for every pair just like we were doing before, except now we're also going to do a nested check for every pipe rather in that actual pipe pair, even though you probably don't need to necessarily do an iteration over the pipes because there's only ever going to be 2 pipes per pipe pair. But this also is a nice opportunity to illustrate nested iteration. So you have 4K pair in this outer loop. So we're iterating over every pair, but within every pair, we're also doing an iteration over both pipes. And so what we can do then is say for every L pipe, and this is just convention, K, L, in V, N, M, just whatever letter makes sense. So we could call this maybe P or some other key if we wanted to. But for every pipe in the pairs of pair.pipes, we'll just use that function that we just defined, and then we're just going to pass in the pipe to the bird, the collides function in our bird class. And then if that's the case, just to illustrate that we actually got a collision for right now, we're just going to set scrolling to false. So if I go ahead and run this. So previously we were just kind of clipping through all the pipes, but as soon as I hit one of these, you'll notice right there, you can even slightly see that it's just like 1 pixel in on the bird too, because remember, we set the, or I guess it would be 2 pixels-ish, we set the box to be just a little bit inside the bird. So this is kind of a slightly more fair way to do collision detection. But indeed, we now do have collision detection. It can collide with the top pipe. We'll do an experiment. Let's collide with the bottom pipe as well. So let's just go ahead and run this again. And then let the random pipes come through and hit this bottom pipe. And you'll see that both pipes in this case are collidable. So now the game sort of is at its core functional in the ways that are important, at least to get us closer to being able to have a score and a game over state. So I'm going to go ahead and transition back here. Which brings me to the topic of state machines. So we had the opportunity last time to talk about state machines a little bit. And state machines, and we even have this exact slide up, but what we want to do is have a more refined way of looking at the transitions in our game. So if you remember last time, currently we don't have many states. We just have, the game goes right into, the bird is falling and we can bounce around and stuff like that. If we want to actually have, let's say a title menu or an intro, or like in Pong, we had the serve state, we had a game over state, we have all these different states. All of these are, when you just have a flag or a string variable that you're using to check, then your main.lua gets really big and complex, hard to read. It's just hard to grok to see, okay, what state am I in? Am I in the serve state? Am I in the high score state? If I'm in that state, what do I need to do? Do I need to do X do Y, whatever? It gets to be a little bit cumbersome. I would say very cumbersome, especially at scale. But there are better ways to model these sorts of things. And so what we were doing is not really much different than a state machine, but we actually are going to introduce a much more effective state machine. But just as a reminder, this is what a state machine looks like conceptually. You have states, which are modeled by these rectangles here, which have terms. So you have ducking, diving, jumping, standing. So this is sort of modeling a platformer state machine. And then you have the transitions between them. So in this case, this is if you go from ducking to standing by releasing down, you can see that relationship modeled there. So we release down, we go from ducking to standing. If we're in standing and we press B, we'll jump, and then so on and so forth throughout the rest of this diagram, which we talked about last time. And this is sort of how you can diagram out the overall flow for your entire game. This is modeling an entity, a character, but you can model anything that changes state and that has state, and that state is important in determining how it should make transitions. This is what our state machine is going to look like for our game state today, and for a while this will be the primary type of state machine we use to overall guide the states of the game. We ought to start in the title screen of some kind. That's typically what games do. If you fire up a game from back in the day, even now, you'll see the logo and like press start to play, something like that. So here, if we can model the relationship here. I've done it through this sort of way of looking at it, or this way of presenting it. But if you press enter when we're in the title screen state, we go to the countdown state. So countdown states, I think, just kind of a fair way to allow us to be prepared to start pressing spacebar when Flappy Bird is running. So if we press, if 3 seconds pass, once countdown state has begun, then we should transition to the play state. And then when we're in the play state, now we're actually playing with Flappy, with the bird, and we're bouncing and we're doing collision detection, we're accumulating points. But if we collide with a pipe, that should transition us to a different state. In this case, it transitions us to the score state. And the score state is just, hey, you scored X points. And maybe you could do something like show the user they got a bronze, silver, gold medal for how well they did, or something like that. And then when we're in the score state, is often the case that at the end of getting to game over, score, what have you, you'll want to allow the user to get back into the game right away. So by pressing enter, we can denote another transition from score state right back to countdown state again. And now we have this sort of infinitely doable loop, we never really ever go back to the title screen, although you certainly could depending on what your game's use case is or what you prefer. In the case of this example, we're just going to go back to countdown, and then, because we already sort of, don't need to remind people that we're in Flappy Bird, countdown state, and then people can just essentially get caught in this infinite sort of triangular loop there. So why don't we go ahead and take a look now at a way to model state machines. We'll look through this relatively quickly because there's going to be a bit of code here, but none of it should be too complex. The important thing that folks should look at or be familiar with is that in main.lua, to start with, remember last time that we did states, we did it in the form of a string. It was just a variable that we were storing, game state equals start, game state equals play, and that can work for very simple examples. But now that we've introduced object-oriented programming, it can be more effective to think in terms of objects. Like, can we represent and encapsulate the behavior of what it means to be in a play state or a score state or all these different states? Because now the benefit of that is they're their own files. They can have their own objects, their own things that they manage. We don't need the bird, for example, when we're in the title menu because we're not moving a bird around, but we do want it in the play state, but we don't want it in the score state maybe. So now each of the states can maintain their own state, their own entities and so forth, keep things a little bit more better encapsulated. So let's go ahead and scroll down here just a little bit. The most important thing that we take a look at is this G state machine. And this is an introduction also to a trend that we'll be using throughout the rest or a convention we'll be using throughout the rest of the course to denote sort of global variables, especially global container variables. In this case, G state machine. So this just means that this is a global state machine. We're going to need this accessible anywhere in our code because especially if we're going to have individual files that now manage whether we're in the score state, whether it's the play state, whatever. If they're their own files, they need a way to transition to the other states. They need this sort of state machine available to them. You'll notice that we're creating a state machine here. Recall this table syntax is just a way to shorthand call a constructor or call any function that just takes a table as an argument. State machine is being required, which is right here, require state machine. You'll notice also we're requiring a few different states as well. And this dot syntax is how Lua does directory, sort of like we have a directory called states within which is a function or is a Lua file called base state. And you do not need the .lua. That's automatically inferred by Lua. So states.basestate just means in the states folder, get the base state file, .lua, require that. And then same thing for these other two states. And then also state machine, which is provided in the distro. So if we come back down here, we have G state machine. And so each state has a key. So a state machine title is going to maintain a reference to, and this is also the interesting bit, there's an anonymous function. We're using anonymous functions. So the benefit of using anonymous functions here is that typically when we have states, we want them to be fresh every time, at least for relatively simple games in particular. Depending on the game, you might want your states to preserve certain aspects of themselves when you're transitioning back and forth. And we'll look at examples of maybe some of that in Pokemon later towards the end of the course when we look at something more complicated called the state stack. For right now, we're just going to look at a very simple state machine, and we just want a new copy of each of these states every time we perform a change between one state and another state. If I'm in the title screen state and I want to transition to the play state, I want a fresh play state. And so what we're going to do is we're going to say, okay, I'm going to define a function here anonymously. This is a thing that certain languages like Lua and JavaScript and Python has lambdas, but JavaScript and Lua will let you do a function actually in line like this and assign it to something. This is called a first class function, or an anonymous function in this case. And so it's actually going to store this function at this key. It's a value, just like any other piece of data. And what this function does is it just returns a brand new state, that brand new, in this case, title screen state or play state. You can put whatever you want in here. And you could have these functions be whatever you want. There's a particular reason why we're returning states in this particular way, and we'll see they have a sort of contract they have to fulfill to work properly. But the benefit of this is that every time we do a change and we call this title with the function that will exist here, we're going to get a fresh title screen state. We're going to get a fresh play state. There's going to be no lingering state anywhere. We're just going to have just like a completely blank slate to work with. And this is of benefit with the kinds of games that we want to deal with typically. So we have a state machine here with these keys that map to these functions that return these new instances of these state classes, which we haven't looked at, these objects that represent these states. We've gone from a state being a variable that's a string variable to being an actual object that we can look at as an object, a little bit more abstractly. But we need to take a little bit more of a look at what these states need to do to implement what it means to be a state. Already you can see right here, right below the state machine, we have this method being called on the state machine called change to title. So all change does is, we'll take a look at state machine in a second to see in the code what it does, but it takes whatever the current state is in state machine, and actually might be better to actually have that open while we talk about this, but change will take the actual state name that we have currently and perform a couple of functions. It'll perform a sort of cleanup and transitional function called exit, and so part of implementing a state means that all of your functions need to have these methods defined as a contract. So it'll call exit on your state, so title, screen, state, exit, whatever that might mean. That can be cleanup, that could be any sort of thing. And then it will now change whatever the current state is to whatever the state name value that we pass in is. It maintains its own state. It's this sort of like self.states, which is this table of as many states as we want. We saw that in main.lua. That's what this is, self.states. It's this table. Then notice that it looks it up by the key, and then it will actually call it with these parentheses here. So it assumes that a function is going to exist there. And so that's ultimately what happens, and that's why these are also anonymous functions here. So these get called and then returned to self.current. So self.current will then have a reference to this object, which is actually a state, an instance of a state, that can then be updated and rendered, which we'll see here. Update dt, state machine update dt, will just update its current, self.current, which will be whatever that object is that's returned by one of those anonymous functions. Same thing with render here. And so now, instead of having to do all this stuff and update and render and have all these objects necessarily do all of that, we can just render the state machine's current, and we'll just defer all of that to the state object itself, and our main will actually become quite a bit more concise, which we'll take a look at in a second. And then here is just essentially a list of empty starting functions that we can initialize the state machine to. If we haven't given it anything, it'll have this, so if we call it, it at least won't crash or anything like that. But this will ultimately get ignored. But this is also a useful reminder of what the functions are, I suppose, that any given state should implement in order to be valid within the state machine. Any state that we create should have a render, an update, process AI, which we'll look at in the future. We're not going to use that just yet. Enter and exit. And these enter and exit functions are important, which we'll also see in a second, for how we can pass data between states. If they're these isolated objects, the question does become, if we're taking all of that out of main and now individual classes, individual objects are maintaining their state, how do they talk to each other? Because if you're in the score state, for example, or if you're in play state, I get a score of 5, and we're just returning a brand new score state, how does it know my score was 5 if they're separate? And that's done through enter and exit. If you'll see, we'll take a look at that in a second, but you'll see when we call self.current enter, enter takes in parameters, and those parameters we can pass in, we can implement a function called enter on our state, which will actually this will be our sort of handshake of sorts between our states to allow us to pass data back and forth between the two. So if we go over here and we just open up, so real quick in main, we'll notice that we've trimmed things down a little bit in our update. So in update, we still scroll things because this is going to happen no matter what state we're in. We want to keep scrolling, but everything else in main.lua in update has been moved to GStateMachine update, and everything has been moved to GStateMachine render in the draw function, except for the backgrounds, because we're keeping those backgrounds. Anything that you want to apply to all states, outside of all states, and still happen, you can do outside of your GStateMachine. But now, if we call GStateMachine update, it's just going to update whatever its currently held state is. GStateMachine render is just going to render whatever its currently held state is. And so now, let's go ahead and look at the states. Remember, we have this folder here. We have a base state with just a few just really empty placeholder functions. Notice that we have init, enter, exit, update, and render. We don't have process AI because we're not using that. But this is a base state. It's just a class with a bunch of empty functions. And then in play state, if you scroll up to the very top, this is something that the class function or the class library gives us. We can say underscore underscore includes equals base state. And what that means is that it will already come pre-loaded with these functions. We don't have to actually implement them ourselves. This is a form of inheritance, which is another object-oriented programming concept, where we can have some sort of subclass inherit from a parent class. So the parent class being base state here. Base state is just like, oh, this is essentially what a base class ought to look like, or what a class or a state that doesn't have any behavior should look like, just a bunch of empty functions. And then we want to inherit all of those. We do that through this underscore 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 includes gets base state. And so in here we have all of the things related to play. All of these things that we looked at before is everything that we put in main.lua. It's just now been taken out. Everything that was updated when we should move and set the timer and spawn pipes and all of that stuff. We'll just scroll through it really quickly. Update the bird. Important thing to note, like we no longer have to keep our bird in main.lua. It's now here in the play state. The play state's the only place where we need the bird. The play state's the only place also where we need the pipe pairs and the timer. So the more you can take out of main.lua in a lot of ways, the better, because now that gives you sort of an easier way to see what's happening at a high level, look at your states, look at some of your top level loaded data, look at your overall flow, and then now I don't have to think in terms of my entire game at once when I'm navigating everything, especially with Pong, when we have all these conditionals and we're doing screen checking to see, okay, are we in serving, are we in the game state, the play state, what are we doing right now? Now all we have to do is just look at, okay, all I'm worried about right now is, do I have things working properly in the play state? And you do. We have an init function, we have an update function, we have a render function. We don't have an exit and an enter function implemented yet, which we'll look at later. That'll be when we get to the score state implementation. But if we look at title screen, for example, this was something that we didn't have previously, but now we can just easily create a new title screen, again, inheriting from base state. So it has at least an empty shell of all the methods that it needs so that the state machine will call the method and it won't be missing. But you can see it has an update, and it's just if love.keyboard.was pressed, the function that we built previously, enter or return, then notice again, gstate machine change into play. And then same down here, we're just doing more rendering, and we're setting fonts to various fonts that we've preset in love.load at different sizes. If we go to, I'm not sure if we took a look at that previously in main.lua, but you can see we just created a bunch of fonts here. These are just pre-baked in, small, medium, flappy, huge, and then we just set whatever font we want. That's what the title screen state is doing. And so in the play state, once we've transitioned to the play state, you can see that if we collide at all, we then change back to the title state. Not typically maybe how you would always want things to be. It's a little abrupt, it's a little harsh, but for the sake of the illustration, it's going to serve us well. So I'm going to go ahead and start main.lua. If we run this, you'll notice that now we're using a couple of fonts. These are just free fonts I found online that look kind of in line with what we want. You'll see what it says 50 Bird, which is themed after CS50, and then press enter. So press enter. Only the state machine right now is loaded just the title screen state, and it's calling update and render on that in main.lua. Nothing is happening at all with the play state. All that code is kind of just almost hidden away effectively. We press enter, and then we go right into the play state. And now a call to the play state has returned that. That's being held in the state machine. And then as soon as we hit a pipe, well, now we're right back to the title screen state again. We used gstate machine change to a brand new version, brand new instance of the title screen state. And if we press enter, we'll notice that it's a fresh copy of that state because there's no pipes. The pipes are gone because we created, remember, that anonymous function returns a brand new version of the play state. And so if we do it again, we'll notice brand new version of the play state. So this is desired behavior in many cases where we don't want, whatever was left behind in memory or whatever could have been left there the last time we were in that state. We just want to essentially get a fresh play field, so to speak. So that is the state machine, probably one of the bigger changes to the code base. So that adds probably one of the more useful and more commonly recurring pieces we'll see throughout the rest of the term. I say that a lot because a lot of these pieces are very useful. But with just the state machine, we can start to add a lot of really cool things very quickly. And so why don't we go ahead and start transitioning through a couple of more states. So for example, we have the title screen and we have the play state, but what if we want scoring to occur? Well, what does scoring even mean? In Flappy Bird, a score is accrued through actually clearing pipes, which I've been having a difficult time doing for illustration. I might have to tweak balance the numbers a little bit in order to actually properly illustrate it. But effectively, if the bird's x coordinate is to go past the sort of the right edge of any pipe pair, which is be that pipe pair's x plus its width, well, we can increment our score at that point. We've effectively cleared that pipe pair as an obstacle, and then we just increment by 1. And so our goal is to effectively just keep doing that as many times as possible, and then whatever that value is should be presented to us ideally at the end of the game, at the end of the run, whenever we do finally have a collision. So let's go ahead and open up bird 9 and look at that really quickly. The beauty of this is that it's relatively easy now. Let's collapse some of these here. It's relatively easy for us. So if I open up main.lua, you'll see that we're importing score state. That's going to be our new state. And again, now we're just modeling states. We just very quickly just add a new state into our repo, into a new object rather, into our folder, and then we can just load it into our state machine. And just like that, now we don't have to add a ton of if statements and change strings and spaghetti wire our code. We just add literally a new key, score, here to our table, and then we set it to return a score state instance. And so we'll change the title as usual. Once we're in title, it'll be the same thing. Press enter to start the play state, and then once we're in the play state, now the important thing is we're going to need to start keeping track of our score. So let's take a look at play first. So we're in play state. So we'll see right away when we're actually updating the bird in our play state, and we're looking at every collision. Since we're already iterating over every pipe pair to do a collision test and every pipe therein, when we're doing that, what we can do is say, okay, if there's a collision, let's just transition to the score state. So that'll be the point at which we collide. That's our sort of game over. We'll transition to that. So G-state machine change to score. You'll notice we're passing in an object in this particular instance, and in the one below here. This is the same thing, except effectively we're just checking if we hit the ground at all. But this object here, if we open up the state machine library itself, you'll notice that change takes in these enter params. So this is a very important thing. This is about, again, how to have one state talk to another state. So the score state, or rather the play state, needs to talk to the score state. Because remember, these are kind of like separated domains, separated areas of play that don't know each other's variables, each other's state. But the score state needs to know the score that we got during our play state. And so to do that, we need to allow any state, but in particular in this instance, the play state, to send a message to the score state saying, hey, this was the score we had at the very end. So we can just take a table here called enter params that if we look here at self.current enter params. So once we perform the exit function on whatever our current state is, so if we're thinking about we're in play and we're transitioning over to score, we're going to call play exit. We're going to set current to now the self.current at score, create a new instance of that, and then we're going to call enter on whatever current now is, which is the score state, passing in the enter parameters that we initially passed into this function. So the score state now is going to get that table, those parameters. If we're looking here, enter on the score state is going to get this table. So this table is going to get passed into our state machine, and it's going to be the sort of like handing over the keys or what have you to the next oncoming state that we're going to transition to. And so once we go over here to take a look again up above here, so we have quite a bit of code here in our play state, but below where we actually are spawning in the new pipe pairs, we have an iteration to see if not pair.scored, meaning that we haven't marked that pair as already being scored, which is a flag that we need to add to every pipe pair, because we could just check every iteration, every single 1/60 frames, 1/60 seconds, and see, or whatever your frame rate is. We could check every pair and say, hey, have we gone past it? And any pipe pair that would be to the left of the bird in that instance would still be to the left of the bird for a while before it despawns. And so we want to not rescore that pipe pair over and over and over again, or our score would very quickly get very high. So we just flag the pipe pair as being scored if we happen to score on it. So we can just say, okay, if not pair.scored, then we're just going to say, okay, if pair.x plus pipe width is less than bird.x, meaning is the pipe pair to the left of the bird? If so, that we've cleared it, the bird's gone to the right of the pipe pair, and so we can just increment our self.score, which is a state variable we're keeping in here, and then we're just going to say pair.scored gets true to store that in the pipe pair, and then that takes care of not only our score being stored as a piece of state, but also prevents like unnecessary rescoring of already scored pipe pairs. So let's go ahead and take a look then at the score state itself. We can see here it defines the enter function. So you don't have to define enter yourself. If you include base state in a state class definition, you will get it just an empty one that will work just fine. This gets called on every state change, so it has to exist. But in this particular instance, it expects that we will be getting those params, and it's going to set its score to params.score. So remember, this is the table that we're sort of transferring over during the state change from play to score in this instance. So self.score gets params.score, so we're going to store it now in the score state. And we can now render that. If we come down here, we'll say your score is colon, and then this is the concatenation operator, and then self.score. And then we can say, hey, press enter to play again. And now we've added, again, that press enter check or return to transition to play once we're in the score state. And so all of the activity related to score state, thankfully, has sort of been kept, sort of encapsulated in its own block of code. So if we go ahead and run this, hopefully I can score at least 1 point. We'll find out. Might tweak some values just ever so slightly. I just have to get 1 point. Ah, damn it. Try one more time. Okay, maybe I'll tweak make it a little bit easier for the sake of my. We'll say it's for the sake of time, but it's really for my ineptitude. That would be in the bird.lua. We'll say dy gets -250. That might be okay, and then we'll just maybe tweak gravity to be something like 900. Try that out real quick. Yeah, that looks a little easier. Let's see. Yeah, got 1. Got 2. Okay, maybe we should keep it at those values. That was actually a little bit more fun. But you can see what's cool is that we got 2 in the play state. That value incremented a couple times, and then it was transferred over through the state machine's change over to the play state or the score state, and it just has it there as a value, and then we can just do this ad infinitum. And this is the process by which you get state that you can transfer between things while keeping them separate logically. You don't have to think in terms of like, oh, these are coupled together really tightly and they have to be, nestled, and you think about all the code in the way that you would in for example, Pong's lecture, which was purposefully done naively with just a simple variable that we conditionally checked, or in any other way. We just can think of things more conceptually as objects for state, which is kind of maybe useful depending on how you want to think about it. And this applies not only just to game states, which is what we're doing it for right now, but this could be for entities. It was used even in our example. It was shown for something like a Mario character for diving and jumping and all these things. And we will indeed use that for when we get to Mario and Zelda in particular. We will use that same idea. So I'm going to go ahead and close that out. And so that brings us then to the idea that, well, we have the score state now, which is, okay, we can score. Our game is relatively complete in most senses, but I mean, it's a little bit jarring when it starts off. And if we're exploring states and it's just easy to add new states, why don't we just add something to sort of give us a better UX, or I guess a user experience, to get us into the game itself. And I'm thinking, you know, a countdown sort of makes sense. It's a little jarring when we just start. For example, I'll show it again here. But when we just start and we press enter and we're just already falling, it's kind of like, oh shoot, maybe I wasn't ready for that. That might feel a little bit fast, a little sudden. So if we just had a simple 3, 2, 1 countdown, well, it's not the title screen, it's not the play state, it's kind of like a lead into the play state. It's kind of between the title screen and the play state. So let's just add our own countdown state to the game with this infrastructure that we've put in place and represent that. So let's go ahead and do that real quick. I'll close all these out. Go to bird 10. And so bird 10, so in the title screen state, you'll notice that we go right to countdown when we press enter. We don't go to the play state. And then when we're in the countdown state, we have a countdown time, which is 0.75. You could tweak this however you want. 1 second felt a little bit too long, but it's about 1 second. It's close to that. We started at the count of 3, and then we have another timer, essentially the same thing that we did last time. And then we're just going to basically say if our timer has gone over whatever that interval was, decrement whatever our actual number of seconds that we want to look for is, which is 3. So once count gets to 0, so at 0.75 dt accumulated will go down to 2, then to 1, then to 0. And then so finally, eventually, when self.count is equal to 0, we can then transition to the play state. And so we'll just always render whatever that count is here in the render function, and then so we'll visually even be able to see the operation of that state working. So let's go ahead and just run this real quick. So see 3, 2, 1, boom. And once it hits 0, we do an immediate transition to the play state. So kind of a nice little softening of the process of getting into the game, which I'm a fan of. The last thing that's missing really, and we saw most of this last time, is there's no sound. I mean, I feel like sound is kind of an important thing to top things off. And so why don't we take a look? We have just a couple of examples left, but this one in particular is mostly things that we saw last time. So I'm going to go over to bird 11, and then I'm going to open up main. You'll see that this has gotten quite packed with files now, and one of the things that we will be looking at is, okay, how can we tidy up our actual project folders, because this is just a little unwieldy. Like, we got a bunch of Lua files in here, we have wave files for sounds, we have images, we've got, now we're going to have multiple folders with source code in them, like this states folder. So we will tidy things up, but for right now, I'm going to go into main.lua. This is going to, if I scroll down just a little bit here, you'll notice I did something like this last week, but we now have a G, again, using the G to designate it's a global table. So we have this G sounds table here. We've got jump, explosion, hurt, score, and then finally a music track. And so the music we're just going to set, in particular, a couple of interesting functions, but it's just play, and then which we saw last week, but also set looping is a function that you can use for audio files. If your audio, typically you wouldn't want this for sound effects. I mean, I guess you could for certain ambient sound effects and things of that nature, but you know, for like obnoxious sounds, you wouldn't want this 100%. But for music, most of the time, you absolutely would want it. And just like we saw looping textures, sometimes you want looping music that is also, it's kind of the same logic where the end of your track is immediately the same as what would be the front of your music track, so that you don't feel this perceived like either audio gap or a harsh sort of like new change in key or change in just overall what this song is doing. But here we're doing it so that no matter what happens, once our audio plays, it's just going to re-trigger. And throughout all the code, all the places that we do various things, there are a bunch of calls to call these. We won't spend the time to track down every single instance, but you know, jump when we press spacebar, explosion and hurt when we hit a pipe, and then score when we actually make it over a pipe pair. Those will just play sounds in the same way that we did last time. And if we run this, we'll see right out the gate, we have audio that's beginning to play, the music, which is just much more fun already. If I press enter, we'll transition in, and then we get little spaces here. I think this is pre-configured with a much easier setting. It's way more fun when you, oh, I didn't even demo crashing out. I probably should do that, okay. Because it's way more fun to not be hitting the pipes. I got so fixated on that. I'll hit a pipe right away this time. Yeah, and so also there's a thing that I am doing in that instance too, where we have this explosion and hurt sound. We have two separate sounds, but sometimes it can work to layer sounds, and this is often used in music as well for good effect. But sometimes if you don't have quite the right sound, it can be easier to just play two sounds at the same time than to try to like synthesize the ideal sound. But that's essentially all that's happening in that particular instance. Now, the very last thing that we have is because Flappy Bird was a mobile game from the outset, and we are using it from the perspective of the keyboard, but it wasn't designed ultimately to be used that way, I thought it was fitting that we might sort of emulate that. And so the way that we can do that is Love gives us this function called mouse pressed, which is very similar to key pressed. It will just trigger any time that you click the mouse, and this is essentially also a deferral to touches on iOS or Android, and this is often how it's modeled too in the web world. But once we click the mouse, it'll essentially fire whatever mouse button we click with. So it'll be like a 1 or a 2 for left or right click. So if we open up the source code here for Bird 12, we can very quickly look at that. It's very simple because it's essentially just one of the Love callbacks. So we'll go over to main.lua, scroll down just a touch here. And we'll see below Love key pressed, we have a Love mouse pressed. So it also takes an X and a Y, which is useful. This will come in handy when we look at Angry Birds in particular, which uses like actual tracking based on where you clicked and moved the mouse or moved the pointer. But in this case, it doesn't really matter what the X and the Y is. We don't care about that. If we just click the mouse, we essentially just want the bird to bounce up and down instead of hitting spacebar. And so all we're doing is we created a very similar construct to what we looked at previously with the keys pressed thing that we added to keyboard. But in this case, we're adding to love.mouse a buttons pressed table. And we're doing the same thing here. You can see love.mouse.buttons pressed. And this, again, just as a reminder, allows us to do these checks for single clicks, single button presses anywhere in our code. We can just think of it as if it was a globally accessible Love implemented function on their global objects, but we are implementing it ourselves by extending their namespaces. And so, and also again, just like, here's the love.mouse.wasPressed, which just takes a look at that table to see was that button actually pressed, and then we reset it in our update function. And so if we take a look at, for example, the bird file, we can see if love.keyboard was pressed space or, so we're supporting either operation here, love.mouse was pressed 1 being the integer that maps to left click on computers, then we do that same behavior, the exact same thing we were doing previously. And you can even see here it also references G sounds. Again, the G being a useful identifier for a global sort of table or data structure or what have you. Globals can be dangerous. You don't want to overuse them, but if you're using a sort of data supply of textures or sounds or what have you, it can be convenient and often the most elegant way to do things. We'll go ahead and run this, and you might have to take it on faith that I'm doing this, but I will just be clicking instead of, I'm clicking right now instead of hitting spacebar. It oddly feels even more difficult. I think this is because I think that it needs to be, they didn't have the balance update in the other source code example. But as you can see, very trivial ultimately to add a left click support feature in your game, especially if you were thinking of maybe exporting it to mobile platforms. And the Angry Birds example, again, we'll look into more information on that and using XY sort of the positional information as well, which can be useful. So we covered a lot of stuff this time. Next time we'll look at a few other things, in particular sprite sheets, which will be next week's is breakout. So sprite sheets will be very useful. The one thing that we did this week, which people might be thinking about, is all of our textures are individual. And again, our actual folder is getting to be very sort of large and dense and full of stuff. So we probably want to find a way to, as much as possible, condense resources, and sprite sheets are an effective way to do that for graphics. So we'll be looking at that. Procedural layouts for our actual maps. So next week's is one of the more fun, I think, procedural quote-unquote generation approaches that we'll take throughout the term. We'll have, I think, what I feel are quite enjoyable layouts for the bricks, but that's maybe getting ahead of myself a little bit too much. We'll be looking at levels, so we haven't had that yet. We've sort of just had like Pong is a game you play back and forth, and then next week we'll do levels. Health, particle systems for more graphic, fun stuff. Fancier collision detection, which is going to be, that's one of the things about Breakout, that based on the direction and where you hit the bricks, it can be a little bit different. And then persistent save data, which actually save your score if you want to show off your high scores in the future. And then for the first assignment, there are a few different things we'll want. So the pipe gaps right now are like a uniform size. And so maybe, or not a uniform size, or they are a uniform size rather, but we want to maybe make them larger or smaller. And so that might add or change the difficulty, for example. If they're smaller, it's going to be borderline impossible. If they're larger, it might be easier, and that might be something you would progress through time, for example, if you wanted to balance the game slightly differently. Same thing with the intervals of the pipe itself. They all scroll in and they all come in at the same time right now, but we could also randomize that. And then maybe they come in staggered, or they're slow, or they're faster, up to you. And then we've done these sort of new states where we could show, like, for example, the score state, but what if we want to, depending on your score, actually have a Olympic medal or something, bronze, silver, gold. Oh, you got a certain number of points, you cross a certain threshold, and it's a good or less good job. And then finally, a pause feature, which is also a great opportunity to use states. But in this case, you might want to also keep things on the screen, for example, Flappy Bird. So it might be a hint in terms of, like, maybe that's not necessarily a state in the sense that we're showing, but some other means by which you can communicate and illustrate state. So that was lecture 1, Flappy Bird. Again, it was a bit of a more modern take instead of the Pong Atari take from last time, and we covered a lot of ground. We went through and totally revitalized, rejuvenated, and reorganized our source code. Rather than having everything be this massive set of conditionals, we now have states that are elegant. We can model things as state machines. Next week, we'll dive into Breakout, which will be a little bit more intricate and visually interesting. But this was lecture 1, Flappy Bird, and we'll see you next time.